Okay, so if you remember, we use extendable hashing in place of hashing. And the idea is that in the ideal case, I'll just write here the ideal case, you only need 2 disk accesses to locate a record. Okay, so you'll require 1 access through for the index. I'll call it the index block, and 1 access for the records block. And the idea, again, is that the index is laid out as though it were an array. So the requirement is that the index, the entries must be stored contiguously on disk. So the entries are stored contiguously on disk. Just like in main memory, the entries in an array are stored contiguously. And that's going to allow you to do a computation that gives you the disk address for the index block you need. So remember that the way an index works is that, well, let me go to the next page. So you have an index, and initially it's going to start with some number of entries. It's generally not going to start with just 1 because you'd be splitting immediately. If you remember, it consists of taking some number of leading bits from the hash key. So last time and this time we're considering hash keys that were 6 bits long. In practice, they're going to be probably 32 or 64 bits. And we had each of them pointing to some, well, I'm going to need, heck, I'm just going to do 4 bits right now because that's what fits. And as you can see, you could have duplicated hash keys. That's okay. You can have collisions. That's fine. You're just storing the entries in contiguous order. And you will have to, if you have a collision, you would have to then disambiguate the 2 keys so that you go to the correct place. So you may have both the, well, it's not true. It's easy. You just, let me back up. In the actual index, this is not what you see. Okay, this is what the hash keys are, but what it would actually be, let's say this was on salary, they would really be like 10,000, 10,000, say 50, 20,000, say 53,000. So what you would actually be storing in the index block is the key value and the disk address of the record containing that value. What I'm showing you is what the keys hash to. So 10,000 hashes to a key that's 0001. 20,000 hashes to a key that's 0011. So it's okay to have collisions among your hash keys. They just end up in the same index block. That's not a problem, because when you retrieve the index block, you're just going to do a sequential search through it to find the address of the key in which you're interested. And because a sequential search isn't going to take you that much time, it's not a big deal. And if it could take a lot of time, you can organize the keys in sorted order and use what kind of search on it from CS102. Binary search. So if it's going to be a real problem, you could always have them ordered within the index block. Okay, so the capital D equals 2, that's the number of leading bits that you're considering. Number of leading bits in the hash key. So right now, we just have our directory is just considering the first 2 bits. If we need to add an entry and we need to split a leaf, so let's say in this case that L is equal to 4. Okay, actually that's kind of wrong. We should really set, it's really the number, yeah, we will say L. So L is the number of entries that this leaf can handle. So we'll say 4. In real life, it's going to handle a huge number because we're only storing keys. So last time we came up, I know that my math was horrible, but didn't we come up with around 500 or something keys that could be stored in a 4096? Yeah, we came up with something like that. In a 4096 byte block, you can get about 500 keys. So in actuality, L would be more like 500. Okay, but for our purposes, L is equal to 4. So let's say we need to add a new key that is 0, 0, let's say 0, 0. So we look at the first 2 bits and we see that it's going to go into that block. But unfortunately, it's full, so we need to split it. What we do is we look at the 3rd bit. So we say, in this case, we have to double the size of the directory because instead of looking at 2 bits, we now have to look at 3 bits. So what we're going to do is double the size of the directory. So we're going to have to rewrite the directory at this point. That's a disadvantage, clearly. So now we're going to be using 3 bits. Whoops, that should be 001. Now, for the leaf that's split, that one needs 3 bits. So we're now considering 3 bits, the leading 3 bits for this particular leaf. So you can see that 4 of the entries start with 0, 0, 0. I'm sorry. Only 2 of the entries start with 0, 0, 0. And then 3 of the entries start with 0, 0, 1. So these are using 3 bits. So capital D is equal to 3, but then each leaf also keeps track of how many bits it's using. The remaining ones only use 2 bits. So the index entries for 010 and 011, they still only have to use the leading 2 bits. They did not split. Same thing for 100 and 101. They both point to the same leaf. And so does the 2 entries that start with 111. Or just, yes, with 1, 1. So these are using 2. So we actually only have 5 leaves, even though we have 8 directory entries. So when we have to, so in a hash table, should it become full, we have to rehash everything. Okay, that's an expensive step. In extendable hashing, if we have to double the size of the directory, we don't have to rehash anything. And we don't have to move records between, these, not records, but we don't have to move index entries between blocks. We split one leaf into 2 leaves. The only thing that we have to rewrite is the directory, which isn't as large. So it does occasionally split. We occasionally have to do a bunch of disk accesses to handle that split, but the splits are very uncommon in the directory. Okay, so for example, we could have another key that we add. Let's say we now add another one with 1, 1, 1, 1. That's going to cause this leaf to split, but it has a bit to spare. It was only using 2 leading bits, and therefore we can simply split this leaf into 2 and then separate these 2 entries so that they now point to different leaves. So we just add a new leaf and move all the 1, 1, 1s over to it. So this one comes over too, and the 1, 1, 1, 0. And we no longer have, whoops, this one goes away, and this, let's see, we had another one move over, 1, 1, 1, 0. So this goes because it moved. The only one that actually stays is the 1, 1, 0, 0. And now we still, whoops. The entry for 1, 1, 0 still points to the old one. 1, 1, 1 now points to the new one, and we update each block to indicate that it's now using 3. Okay, so the splits are pretty uncommon. Also remember the leaves, they can hold up to actually probably 500 keys. So when they split, they're still going to have, on average, 250 keys each. Now, unlike B trees, where you allocate exactly half to one leaf and half to the other, with extendable hashing, it's never going to be quite even because, as you saw with the second block, 4 of them ended up going to one and only 1 went to the other one. And that's because of the random nature of the hash keys. But as long as the hash algorithm is pretty uniform, you won't be too far off for very large blocks. So maybe for very large blocks, you might have 230 going to one and 270 to another. Okay, and the book does talk about the possibility that when you do a split, that all of the keys go to the new leaf. So if this 1, 1, 0, 0 had, instead of had another leading 1, it would have ended up over there, and we would have had to split yet again. Okay, and then we would have had to increase the size of our directory from 3 to 4 because we would have had to consider the 4th leading bit. So you actually have to consider this case in an extendable hashing algorithm. The chances that a split, that all the keys will go into one leaf are vanishingly small, right? Okay, if you have 500 keys and it's uniform, what's that probability? You can give, someone heard it. Actually, it's a whole lot worse than that. You're close though. You kind of are on the right path. Give me, it's an exponential. You can't compute it. Pardon? 0.5 to the 500, right. So each one has a 50% chance of going into either one, right? Because it's uniform. It's a coin flip. So for all 500 to go into the same one is 1/2 to the 500th power. Okay, that is a vanishingly remote possibility. But you still have to consider it in your implementation. Not all the time will your leaves be able to accommodate that many keys. Okay, so this is pretty simple. If you're doing a lookup, and let's say it maps to 100 is the leading 3 bits, then you know where the first entry starts on disk. Let's say it started at location 1000. So this is 100 is 4. So you would end up adding 4 times whatever the length of a key is. Okay, so it's roughly 8, 4 bytes for the key and 4 bytes for the pointer. So that's going to be 1032, and then you just divide by whatever the size of a block is. Maybe it's 4096, so this would still be in block 0. Okay, but it's just like an array. So with once you have the hash key, you can immediately calculate the disk address of your index entry. Then you'll go and retrieve the index entry. You'll do a linear search or a binary search. You'll find the key and a pointer to its disk address, and you're good. Okay. Now, in the book, the handout I gave you, they were saying that you might store the record in the leaf. In a database system, that will probably never happen because the extendable hash is probably always going to be a secondary index. So all you're storing is the key and an address. It's almost always the case that you're going to use either a B+ tree to do clustering, or if the relation is so small that it's not worth it, you just use a heap. So it's very unlikely that your file is going to be ordered using an extendable hash table. Therefore, it's hugely unlikely that you're storing actual records in the so-called leaves of an extendable hash table. Does that make sense? So the caveat that the book had about, well, if the records are too big, you could just store the keys in the leaves. That's exactly what the database system is doing. It's storing the keys only. And you'll hear people call these buckets after traditional hashing, but they're also often called leaves because it looks like a tree, right? It's just a very low level tree. The other thing is that it's rare that you're actually going to be able to cache the entire index in memory, but you will be able to cache some blocks. So some accesses will require a single disk access because you'll only have to access the record. Sometimes this may be cached already in memory for you. Not always, but all database systems do a bit of caching. But it certainly allows you to get any record with just 2 disk accesses. Okay, so questions about that? Okay, actually that's wrong. That was wrong. Let me restate that. This is one disk access. This is two disk accesses. So the third disk access may in fact be to get your record. And it is this one right here that parts of it may be cached in memory. But this one itself is also sitting on a disk, and you're doing a calculation. So your first disk access is going to be to get one of these entries. Your second disk access will be to get the leaf, and then your third disk access is to get your record. So it actually is two disk accesses to get the address of your record, but it is three disk accesses to actually retrieve the record. And a large chunks of this first level, so large chunks of this first level may be cached. So you may get away with two disk accesses total. Okay, is that clear? So even that top level directory is not actually in memory. It is on a disk. Okay, so three disk accesses total. Two disk accesses for the index, one disk access for the record. That's still less than a B+ tree. Remember last time it was at least 4 accesses. Okay, so questions about this. We're not going to worry about deletions. We're only going to consider insertions. Okay, so the two big questions then are, how many leaves are there on average, and how big does your directory get? Because this isn't going to be feasible if D is equal to, say, 30. Right? 2 to the 30 is an enormous number. So this scheme is only going to work if capital D does not get to be too big. Okay, and then the other question is, what is the average number of leaves? Here we have 6 leaves even though we have 8 index entries. So the top level directory is typically going to have far more entries than leaves. So the questions for extendable hashing is average number of index entries, or directory, I'll call it of directory entries, and average number of leaves. Okay, and it requires some excruciating mathematical analysis to do it. And in fact, when this paper was originally published, I think it was in the 80s, the description of the scheme just took a few pages, and the mathematical analysis took most of the rest of the paper because it was just real hairy. It involves all kinds of probabilistic analysis. But let's see where it is here. Okay, so the expected number of leaves, if you have, whoops, oh, I never knew I could do that. That's cute. Huh. Okay, you learn something new every day. Okay, so let's say that there are n records, and now instead of saying that there is L, well, we'll say L keys per leaf, then we can answer the thing. On average, the expected number of leaves is n divided by L times log 2 of E. Okay, and what does that come out to? Something like Can someone do that calculation quickly? It's rough. It's the inverse of whatever that number is. 1 point, whatever 10 divided by 7. It's about 1.43 maybe? Because 3/7 is about 1.42. 1.4256. What is it? 1.45. Okay. So this is about 1.45. So it's about 1.45 times n divided by L. So the leaves, that means that on average, the other thing that we can say is it means that on average, average leaf is 1 divided by log 2e, or 0.69 full. So on average, they're 69% full. Turns out that if you do that same analysis for B+ trees, that number is almost identical in terms of fullness. So also, they tend to be about 0.69 full, which makes sense because in both cases, we split when the leaf is full and we split the leaf in half. So it makes sense that they come out to be roughly the same level of fullness in either a B+ tree or an extendable hash table. The surprise is actually on the average number of directory entries. Remember, it seemingly could get very big, and that's a worry. But in fact, that number is order n to the 1 plus 1 divided by L divided by L. So that's a 1 divided by L. Okay, so as long as L is pretty big, like say 500, didn't write this out too well, but as long as L is quite large, then this is roughly, no, I'm not getting it well, it's roughly n divided by L, which isn't horrible at all. Okay? So the average number of that's not the average number of bits, that's the actual average number of directory entries. So as long as you pick L to be quite large, the directory doesn't tend to get that big. As long as your hash function randomly distributes the keys. Okay? So, questions about any of that? Okay, so one more time, we tend to use extendable hash tables for secondary indices because those are good for point queries. We use B+ trees for the cluster index or the primary key index because then we want to store the records contiguously, and they are good for range queries. Okay, extendable hashing does not store records contiguously based on a key. The whole idea with hashing is it randomly scatters them throughout memory. Okay? Yes?
So you said earlier that primary keys were not
usually used. So it would be quite rare to have a primary key index. So you normally choose one attribute to be your so-called cluster attribute, the one that you order it on. If it happens to be the case that the cluster attribute is the primary key, we call it a primary key index rather than a cluster index. But so I'm careful to make that distinction because the book makes that distinction. But you're right, because the primary key is usually an artificial key. It is really uncommon to have a primary key index. It is usually the case that you cluster on some other attribute like salary or time or last name. So usually it's a cluster index.
So, primary key index on an artificial key doesn't exist?
It would almost never exist. Because with an artificial, the point of clustering records on a key is because you think you're going to have some kind of range query, like I want all names that start with S. And if you have artificial keys, it doesn't really make sense to say I want all people who have a social security number between 0 and 100, right? Because they're just artificial. It's not going to really make.
But I thought you would put an index on them because they're using joins.
Yes. So then you put a secondary index on them. Okay? So usually there's a secondary index on a primary key. But then it's not called a primary key index anymore. Confusing, yes? Only if it's physically organized on the primary key is it called primary key index. I hate their terminology, okay? But I'm just going to be consistent with the book. So, because I think it is confusing. Okay, yes?
Is there a way to specify indexes in MySQL?
How do you?
Yeah, how do you specify index?
It's a good question. None of my databases have ever been big enough. I think that there is something like a create index command, but I'm not 100% sure. Here, let's Google it quickly. MySQL index create command. Create index. I was right. Create unique full text spatial. Look at that. All these possibilities. That's how you do it. Okay. Other questions? I won't test you on that. Other questions? Okay. In that case, we put aside databases, sweep them aside except for the test on Tuesday and for your homework. Remember, homework this week is due on Friday, not Thursday, but you're not allowed to submit it late because I want the, nice. Wow, look at that. Uh-oh. That seems to be the problem. Yeah, so at any rate, I want to be able to release the answers so everyone can look at them over the weekend. Okay, so moving on into scripting languages. Do we have it? Nope, I have to open it. Okay, so the whole point of scripting language is to allow a programmer to quickly and efficiently accomplish a task without a concern for machine efficiency. So everything about a scripting language is geared toward the convenience of the programmer rather than the convenience of the machine. Whereas a traditional compiled language like C or C++, even to a great extent Java, are more geared toward the convenience of the machine, toward being able to specify your program in a way that will allow the machine to execute it efficiently. With scripting languages, machine efficiency is a secondary consideration. We want to be able to create our program as quickly as possible. It means that typically either we are programming for a one-off task. So maybe we're writing something and it's going to take, when we're done, it takes us 5 minutes to create the script and it takes the script 2 minutes to run for a total of 7 minutes. So 5 minutes to create, plus 2 minutes to run. Whereas the corresponding C program might take, say, 15 minutes to create. That's probably generous. And it takes, say, 5 seconds to run. So clearly, the C program is more efficient. Okay, but for your one-off task, it took you 7 minutes to get your result versus 15 minutes and 5 seconds for the C program. So clearly, it was in your interest to use the scripting language, and even though the scripting program took about 24 times slower, you got your results 2 times quicker. Now clearly, this isn't a winning long-run solution if this program is going to be run many, many times. If, for example, this program is meant to support an Amazon server, then we need to write it in C because we need it to be efficient. So you use a scripting language either when it's a one-off task and the machine efficiency isn't really important, or when the script is so small that the efficiency you would gain by programming it in C or a compiled language is immaterial. So if you have a script that runs in 0.1 millisecond versus, say, 10 microseconds for a C program, you may not care, in which case you'll still write it in the scripting language. So there's a number of characteristics of scripting languages that separate them from compiled languages. The first is economy of expression. Now, C and C++ also go for economy of expression, right? Int rather than integer, bool rather than boolean. That's small potatoes compared to what scripting languages do. Scripting languages try to give you high-level data structures, built-in data structures like hash tables and lists that allow you to express things more concisely. They give you new forms of loops that we'll see that allow you to iterate over lists and hash tables without the cumbersome for loop notation you have in compiled languages. So they're all about coming up with programming constructs that let you create programs that are as small as possible. Okay? They also allow you to save time by doing away with variable declarations. In a compiled language, even Java, you have to declare your variables and their types. Not so in scripting languages. In some scripting languages, it's optional to declare them. In none that I know of do you actually declare a type. So that's point 3, which is that scripting languages typically allow their variables to be dynamically typed. That means the type of a variable depends on the type of data that it's currently storing. So you might say A equals 10 at one point, and another point you might say A equals Brad. So when A is assigned the value 10, it is temporarily an integer variable. Later in the program, when you assign it the text string Brad, it becomes a string variable. That is called dynamic typing. So the type of a variable depends on the type of value it currently stores, and it's allowed to store any type. Whereas in a compiled language, you are constrained by your type declaration. If you declare something to be a double, well, it can store a floating point number or an integer, but that's it. It can't store a string. It's not allowed to store a char. Can't store an array. Can't do any of that. Okay, so your variables are much more flexible in a scripting language. Okay, many scripting languages, not all, give you easy access to system facilities. So the first language we'll consider, Perl, makes it easy to call out to the operating system to, for example, list the directory contents, or to move files between directories, or to fork off a thread. So they give you easy access to the underlying system facilities. They typically have sophisticated pattern matching and string manipulation, something that C and C++ do not provide. Does anyone know why C and C++ do not provide very good string manipulation? There's a very good reason why they don't provide it. Doesn't have to do with the way they're stored. Good try, though. It's because they were designed originally to create operating systems. Ken Thompson designed C to create operating systems. Operating systems don't require a lot of sophisticated string manipulation. They might shuffle strings around, but they're not trying to locate patterns within strings. Operating systems typically aren't verifying dates. They're not trying to extract information from strings. So they didn't care about fancy string manipulation, but scripting languages typically do. Okay, if you're doing a scripting language that works with web pages, it's all about being able to extract information from the text. So they provide sophisticated ways to manipulate strings and to find patterns in strings, like find all social security numbers in a string, find all dates in a string, find, and you might say, well, why would I ever do that in a string? Well, you suck an entire file into a string and then you search for all dates in that file. You do it by searching for all dates in the string. Okay, then as I said, they provide high-level data types that are built into the syntax of the language. Almost all scripting languages provide high-level built-in support for lists and for hash tables. That's not what they call them. Typically they call lists arrays, and they typically call hash tables dictionaries or associative arrays. But for us computer scientists, what they really are high-level lists, or they are lists and hash tables. Okay? They are interpreted as opposed to compiled. That is why they run so much more slowly. Okay? They often run 10 times more slowly. It's usually the rule of thumb. But the interpretation means you also get immediate results when you run it. You don't have to compile it. Compiling takes time, especially when you have large systems and have to recompile and then relink everything. That can take a lot of effort. Whereas when it's interpreted, it just immediately starts executing and you immediately start getting results. And it's quicker when you're debugging because you're immediately seeing what your errors are. Now, because it's interpreted, it doesn't do sophisticated analysis of the code, so it can't do any kinds of optimizations. Because there's flexible dynamic typing, even if it could compile, it wouldn't be nearly as efficient because a lot of efficiency in a language comes from knowing that if I do A plus B, I can substitute for plus a machine instruction for an integer add or an floating point add or for string concatenation. But if I don't know what the types of A and B are, I can't compile in a machine language instruction to handle it. So even if I could compile a scripting language, the lack of variable declarations and of type declarations means that many of the compiler optimizations that I could normally use are thwarted anyhow. So I wouldn't get a huge speed up even if I could compile them because of the lack of type declarations. So you may not realize it, but a big reason you do type declarations in a language is to help the compiler with optimizing the code. Now, it also helps catch bugs with inconsistent use of variables or with using undefined variables. As we'll see, scripting languages won't even chirp at you if you try to use an undefined variable. it will just give it a default value. Okay, which can be bad because you may start getting results that seem nonsensical, and if it would have just told you it was an undefined variable, you would have been able to fix the problem much more quickly. Okay, the other thing with scripting languages that I don't have up here anymore, I used to, but I don't do it anymore, is garbage collection. So scripting languages don't have you deal with memory. And some compiled languages like Java now use garbage collection, so I dropped it because I figured it was confusing. But scripting languages pretty much uniformly use garbage collection and don't allow you to allocate or deallocate memory explicitly. They do it for you. Okay? Even Java still has the new operator. You won't see that in a scripting language. The allocation of memory is just done under the covers. When you create data structures, they just automatically allocate memory. But all of these features that you see there are aimed at economy of expression. So it probably would have been good to say that the overarching goal is to save, would be to save programmer time through economy of expression. And then the remaining things here are all the ways that we achieve economy of expression. So these are all ways to achieve economy of expression. Okay, it turns out, for example, that being able to use something called regular expressions to do pattern matching is a very programmer efficient way of being able to find patterns in strings. It's not so efficient from a actual program execution standpoint. So really, the first bullet there is the overarching goal. The remaining bullets are the way we achieve economy of expression. So questions about that? Okay. So, as I said at the beginning of this class, we're going to consider 3 languages, scripting languages: Perl, PHP, JavaScript. Perl because it is widely used, kind of used as a general purpose scripting language, and very good for extracting information from files and organizing it into reports. PHP because it's the primary language used for server-side scripting. It was actually designed to do server-side scripting. And JavaScript because it is the primary scripting language used to do client-side scripting. It also was designed specifically for client-side scripting. And PHP and JavaScript are in some sense more limited than Perl because they were aimed at niche markets, whereas Perl, it wasn't, when it was designed, it kind of was designed for a niche market, but the way it was designed meant it could be used as a general purpose language, and people quickly glommed onto it. Okay, so I am going to go over, kind of in a blitz way, the initial features of Perl today, the variables, data types it supports, operators, and then we'll go into the more novel features of Perl over the, well, after fall break, to be honest, because we have an exam Tuesday, then fall break. So you'll notice that for today, there's actually a couple of lectures that you can look at. So if you want to go through it more slowly, using a lecture than what I'm going to go through it right now, feel free after class to look at the lecture entitled Perl Introduction. And there's also a slower version of what I just went through, Scripting Language Intro. But the scripting language intro won't really say anything different than what I just did. Okay, so Perl was developed, actually, it says here in the mid-'80s. I thought for some reason it was in the late '90s, by a person named Larry Wall. He wanted to be able to quickly extract information from files, organize them into reports. And so he took what he thought were the best features of a bunch of Unix utilities like sed, awk, grep, combined them with a C-like notation, put it together, got his language. And he also made it interpreted, which turned out to be something people really liked because it allowed them to write quick and dirty programs, whereas C, which was the primary language people were using at the time, very low-level language in the scheme of things. It can take a lot of lines of code to accomplish the same thing that you could accomplish with a few lines in Perl. So Perl also became rapidly a favorite of system administrators because Larry Wall built into it access to shell commands. And for Linux or at the time Unix administrators, that was a big win. It was a lot easier to manipulate things using Perl than it was to use shell commands. One of the reasons is that Perl was designed to run on many different flavors of Unix. One of the big frustrations for Unix administrators is that there are many different flavors of Unix and now many different flavors of Linux. And Perl, all you needed was for the interpreter to be compiled to run on a new flavor of Linux, and then it worked. Perl gives you access to the system level facilities through Perl's own syntax. So Perl has its own, has its own built-in commands for getting access to system functions. So let's see if we go down here to, let's make this smaller for a moment. Actually, nope, we can't make this smaller. Yeah, I guess I don't really go over it anymore. What I was trying to find was the Perl command for a directory. I think it is dir, but I'm not positive. At any rate, Perl, we'll assume for the moment it was dir. Perl gives you a bunch of commands that are operating system independent and allow you to do system things like list the contents of a directory, move files between directories. But because it's independent of the operating system's commands, you can run it on a Mac or on Windows or on Linux, and your scripts will work. And so system administrators love that because they just write their system scripts in Perl's language, and then it will run on any flavor of Unix or on Windows or on a Mac. So Perl also quickly became the choice or language of choice for system administrators. Also, as new technologies came along, like the World Wide Web or GUIs, Perl was initially used for them as well. So early on in the history of the World Wide Web, Perl was used a lot for server-side scripting, but it's kind of awkward to use for server-side scripting. It wasn't really designed that way. So PHP was developed, which was specifically designed for server-side scripting, and once it became mature, it supplanted Perl. Same thing with GUI scripting. Initially, it was the only game in town, so people used Perl, but then other languages like Jython, which is Java merged with Python, and Tickle became, were specifically developed to write GUIs, and therefore, again, Perl got knocked out of those niches. So these days, Perl's widely used for two things. report generation, so data extraction and report generation, and by system administrators. Those are its two big claims to fame these days. It also, as we'll see, was the first to really popularize regular expressions, and they're used to extract information from strings. And almost every succeeding scripting language, it bases its regular expression model on the Perl model. Okay, so advantages and disadvantages of Perl. So Perl puts together a lot of the best features of a number of Unix utilities, like the shell, sed, grep, awk, tr, and c. Okay, so that's really its good feature, and it's interpreted, and it has all the characteristics of scripting languages that I laid out in those bullets. Its disadvantage is that Larry Wall wasn't really concerned with readability. Okay, Perl is a nightmare to read. If you come back and look at your Perl program after a month even, chances are you will have trouble reading it. Okay? Perl has been called a write once, read never language. Okay? So its syntax is just about the most hideous of any of the scripting languages that have been developed. And it's not surprising. In some sense, Perl is version 1.0 for scripting languages. And designers learned from its mistakes. And one of its mistakes is that its syntax is hard to read. Okay? Well, Larry Wall wasn't concerned about that. He just wanted to write quick and dirty scripts. He wasn't interested in having his scripts stick around. The problem was his language was so useful, other people decided, this is great, but I want something that's going to stick around, and then there was a whole generation of poor programmers stuck having to maintain this stuff. Okay. The other problem with Perl is he often gives you 5 different ways or more to do the same task. Okay, that's great, except that I do it one way and you know another way to do it, and you look at my code and you're looking at it and you're like, what the heck did Dr. van der Zanden do? And now you're sitting there Googling, trying to figure out what the heck I did, and now you're, losing a lot of the benefit of the economy of expression because you're wasting your time trying to figure out what I did. So it's great if you're just writing a one-off script, but if you're writing something that other people have to maintain, it's hideous syntax, and the fact that you can do one task so many different ways means you actually throw away much of the advantage of programmer efficiency. So that's why it says minuses Perl is a jumble, and why Dr. Planck's colleague said Perl is a brilliant mistake of a kind being repeated over and over again today. At any rate, I'm not going to get into the religious arguments. It can get pretty hot and heavy with people arguing it both ways. Okay, so you can run Perl either using the interpreter. So on our systems, you access it using the command Perl. Then you give it the name of the Perl script and a set of command line arguments. And you can also actually turn it into an executable file by putting this line at the top, #bang, the location of the Perl interpreter, and then your Perl code, and then changing the permissions on the file so that it becomes executable. This only works well in Unix. It's not portable because Perl tends to be placed in different directories on different Unix systems. So it tends to work well on if all you're doing is creating it for your personal use. But if you think it's going to be used globally, you generally don't want to try to hard code where to find the Perl interpreter. You just instead will run it using the interpreter. You also can use it as a command line interpreter. So if you just do D for debug, and then E, which takes an expression, in this case 1, you get a command prompt. So then I can do things like experiment with certain commands. Okay, but it's only good for doing simple experimentation. It doesn't work well. It's not like Python. Python was designed so that you could work with the command line interpreter and get stuff done with it. Perl wasn't really designed with that in mind. That's more for debugging. But if I just create a local file, vifu.pl, okay, $A equals 20, 10, $B equals 20, $C equals $A plus $B, print $C equals $C \n, and I run it, I get C equals 30. So that's what I mean by running the interpreter. Okay, so as I said, I'll let you read most of this because I don't find it to be particularly difficult to follow. And in order to do the quiz today, you'll probably have to read through this before you start doing the quiz. So the syntax is very C-like. The comments aren't. The comments start with a # rather than // or *. Thank you. Your statements end with semicolons, just as they do in C. There's 4 basic variable types, what are called scalars. They hold scalar data like numbers. Strings are considered scalars. Booleans are considered scalars. Chars are considered scalars. There's arrays, which are effectively lists. There's hash tables, which are also called dictionaries or associative arrays. And there's references, which are essentially pointers. So even though you don't declare variables, you tell Perl what the type of the variable is with a letter that prefixes the name. So a $sign prefixing the name means it's a scalar variable. An @ means it's an array. And a %sign says that it is a hash table, which is kind of annoying. Other languages don't have that. It's annoying because you can create $x equals 10, @x equals, say, 10, 20, 30, and #x, is that right? Am I getting the hash table right? Something is, make sure that's, yeah, I got it right, okay. So #x equals some hash table. And now you have 3 different definitions of x, all of which are valid. Okay, I don't think that's a great idea. I would have just preferred they leave those symbols off the front, especially because I seem to do it a lot, thus getting error messages. So as I said, strings are considered scalars, and you can also, with strings, you have double quotes, single quotes, and these back quotes. Each does a different thing. The back quotes give you access to the native system shell commands. So in this case, ls will execute. It will return whatever is returned by the native shell command. Okay. If you put something in single quotes, you get literally what you put in single quotes. If you use double quotes, you get what's called variable interpolation. What that means is that you can put the name of a variable inside of the quotes, and it will replace the variable name with the value of the variable. So here it says $dog equals collie, Then I have the double quoted string, I love my $dog, and it will produce the string, I love my collie. Okay? I did that in this little program that I just wrote here, whoops, here as well. I said print C equals $C \n. It interpolated the value of C, which was 30, into the eventual string. Yes?
Escape characters are stored normally in single quotes, right? Like \n would still work in single quotes.
No, it does not. So watch this. We'll print it again, and we'll just use single quotes, okay? Notice how it didn't work. It both literally printed out \n, and I did not get a new line, nor did it interpolate. So nothing works inside of a single quote. It's literal. The only thing you actually can't put inside of a single quote is a single quote. If you want to use a single quote, you actually have to use double quotes. Okay, because even / single quote doesn't work inside of a single quote. Okay, so you can interpolate scalars, you can interpolate arrays, you can interpolate values of hash tables. Okay, I see my time is up. So before you do today's quiz, read the notes. Okay, they're not hard. They're pretty straightforward. Okay, you still don't think you know what's going on? Look at the video lecture. Okay, and then do the quiz. You got 48 hours to do it. Okay, I will actually finish some of this stuff. There's only a couple things I think are really hard. I'll go over them on Tuesday. No, I won't go over them on Tuesday because we have a test on Tuesday. I'll go over them in a week and a half. Okay, so I'll see you on Tuesday. Study hard, study